I hope that's recording, so we will see. Looks like it is. All right, is everybody ready? Yes, this is CS 537. You should probably know that already. If it's not, if you weren't expecting CS 537, you have two choices. One is to leave now and make it obvious to everyone here that you were in the wrong class, wondering why it said CS 537 there. Two, you can wait and have one lecture about CS 537. This is up to you. My name is Remzi, and my last name is more complicated, Arpaci-Dusseau. So you can just call me Remzi, that's fine by me. It's the easiest part of my name, I think. I've been a professor here for about 22 years, which means I'm old. And, but for that whole time, I've been teaching operating systems and related topics. And so it's the work that I do research in. Some of our best ideas have ended up like in Linux and other production systems. Most of our ideas, we're still waiting for people to discover their brilliance and incorporate them into their systems. So that's the area that I do research in. And I also teach this class and some graduate level classes. And so it's, I'd like to say welcome. I'm all glad you're all here. So what we're going to do today is just get right into it. And thank you for coming. Of course, it's a bit of a strange semester, but we're just going to see what happens. Hopefully it's all good. And what we're going to do today is we're going to do a few different things. And most of the classes will be structured like this, lectures, that is, where we just have a few questions we're going to answer. And those questions are going to structure the entire lecture for us. Okay? And of course I expect this, even though it's a large class, I expect it to be interactive. If you have questions, raise your hand. I'll call on you. I'll try to repeat the question so it shows up in the microphone, everyone can hear it. And we'll just kind of go from there. So feel free to interact in the way that's natural for yourself. And like I said, I'm trying to basically make sure that using the technology available, that this is all recorded. So I will then upload it to YouTube. It actually gets transcribed, etc. And should have a, you can also have a caption track on it and be able to look at it later. So let's talk about what we're going to do today. And the iPad is necessitated by the fact that I want to record this. Normally I would just use the chalkboard, but that's an old-fashioned technology, alas. So, first question. How do computers work? Now, you should kind of already know this. This is just background, right? So we're going to do this first. And as you can see here, I'm recording this in a note. This will be a PDF. I'll also share this with you. So I absolutely encourage you to take notes as we go because it actually just keeps you more interested. It's a good habit in a class is to scribble things. So we'll do this. How do computers work? Then we'll basically ask a question. What is an operating system? Obviously, you're taking this class because to some extent, maybe you don't really know what an operating system is. I mean, of course, you kind of know because you use one all the time. Anybody who uses a modern computer system uses an operating system. So that's fine, but we're going to get into the core of what are the key parts of an operating system, and we'll look at some code there to get an idea. Question 2. Question 3, a question you might have is, how does this class work? So we'll just go over the structure of the class. How we're going to do lectures, how we're going to do discussion. Thursday is our power day, where we have a lecture. We have a very brief break, and then we have a discussion. The discussion in here is me talking about the project side of the class. So Thursdays are going to be very special. We're going to like spending time on Thursday. What else would you be doing on a Thursday night rather than operating systems? I'm not, okay. I guess the people are already giving me some ideas, and it doesn't seem to be as studious as I am hoping. Some people tell me Thursday is when the weekend begins. I've also, in fact, as I remember, as an undergrad, I was an undergrad at a different Big Ten university, which I won't reveal now, but you can boo later. And at that university, one of my best semesters was when I structured my schedule, so I only had classes Monday, Tuesday, and Wednesday. It was the best semester of my life. I had a 4-day weekend. I recommend it if you can. Unfortunately, I can tell from the fact that you're all here that you have not achieved such a high level as I did as an undergrad. So you can have something to aspire to. So anyway, we'll talk about how class works, how lecture works, how discussion works, what the material is, how projects work, how exams work, all that stuff that we have to do to have a class. And then we'll end with kind of just like a, final words. And in the final part of some classes, we'll just have a little bit of wide-ranging discussions from all sorts of topics, usually just a short ending to class. And today we'll talk a little bit about some of the history of what I've gotten out of this class in teaching it for many years. Okay? So why don't we just get into it, and as you have questions, we'll get going. So first question, this one. Let me see how this works. Look at this. Is this going to work? Copy. Oh my God, this is amazing. Okay, you're not going to be as amazed as I am. Oh, that almost worked. Yeah, look at that. Okay, so you can not be amazed. How do computers work? How do programs run? You should have learned some of this. What classes have you taken already where you should have kind of learned how a computer works a little bit? You're like, I don't remember. That is one answer. What's the class? 354, yes. Maybe 252. Maybe you had some programming too, like CS what? What have you had so far? 300, 400, etc., right? So you should have some idea. And when we think about a computer, we think about a few pieces. And this is, again, just background, but it's good for us to review. One piece, CPU, central processing unit. That's where all the interesting stuff happens. Instructions are executed, right? And to some extent, we can almost have a very simple model of a computer system. I ran out of room there. I wanted to write memory. It's like, when you're a child, you do that all the time. You're like writing out letters, you get very excited, and then you hit the edge of the paper because you didn't plan ahead. That is what happened to me. I will now write this and then draw the box. So we have a CPU and we have memory. And by and large, we can focus on that. Of course, there's other parts of the computer system that we're going to talk about, and we'll add those in a second. This is all, again, pretty obvious. They're connected in some way. And when we think about how a computer works, how would you explain it to somebody? Let's say somebody asks you. This never happens, because basically people don't want to talk to computer people. This absolutely never happens. If it happens to you at a party, they say, what do you do? And you start explaining, it ends the discussion very quickly. I've had this experience repeatedly in life. I'm very unhappy about it. This is, by the way, in contrast to people in this building. When they say they're a psychologist or something like that, tell people are so fascinated. You work with the brain and they have their own opinions. When you work on computers, you're like, I work on operating systems. They're like, okay, and then they go over that. So this is our burden for making the world work on computation. So if someone asks you though, and you're trying to make it sound interesting, and they're saying, hey, I heard about computers. How do they work? What would you say? Who will boldly suggest something? There's a lot of people in here. Some of you are bold. Who will say how a computer works? Yes?
Like a second brain. You have like a core memory, and then you have like a some smaller working memory, and then you have like some small part that can fit all the thoughts.
Okay. So you said it's going to be like just so people can't hear probably because we're all masked and nothing works anymore. But what the answer was, it's like a second brain and memory, and that makes it sound way more interesting. Let's go down a level and talk about like 354. Yeah.
CPU does instructions on memory.
CPU does instructions on memory. I like that. Okay, let's go with that. Instructions, which are done or execute. And there's actually two interesting interactions with memory. In fact, this goes to the basic way that we design computer systems. Right? It's kind of obvious that inside the memory there are two things. One is data that we're going to operate upon, and then two are the actual instructions themselves. And some people, we call this the von Neumann, I think it's two N's, architecture, because famously when people were figuring this out years and years ago, John von Neumann, who was a famous thinker, mathematician, kind of a polymath, which means he did lots of things. He invented like some of the basics of game theory. He was had lots of mathematical discoveries. He worked in physics and the atomic bomb. He was an advisor to presidents. And he also at some point realized computation was going to be a big deal. And he talked to a lot of people, and then he wrote a famous article taking everything he'd learned, because he's a really smart guy, and summarizing it. And because of that, we call it the von Neumann architecture, where the instructions themselves, which now that I look at this, my handwriting looks a lot worse than I thought it did. So we'll try to write more neatly. The instructions themselves live in memory, and the computer, the CPU, takes the instruction out of memory and then figures figures out what to do, and then may operate on data, may update some data, et cetera, et cetera. And so von Neumann actually gets a little bit more credit than he should, because a lot of people contributed to that thing, but he just put his name on the report. So there's our first lesson. When you write something down, just put your name on it, and that's how you guarantee you get all the credit for it. Sad story about von Neumann. But anyway, brilliant guy. Good story for him, I guess. So instructions that operate on data. What are some examples of instructions? What's your favorite instruction? Yeah. Load, store, sure. Load, get something from memory into the CPU. Store, put it back. What else? Jump, add. Look, these are pretty boring sounding things. Add, subtract, multiply, maybe, right? Sometimes you can, some architectures are so simple they don't even include multiply. They say you can do that with a bunch of adds. Loading and storing, and of course critically branching, right? The ability to look at something conditionally or non-conditionally, like to a function call, and go do it. Now, isn't it amazing that everything that has been done in computer science and the computing industry that's transformed the world eventually comes down to load, stores, adds, subtracts, jumps. So basic. Anybody can understand that. So basic. But that's what we have, these simple executions, simple instructions. They're just amazing because you can do billions of them every second. Something that actually, it's very hard for us to even appreciate. Like I have a hard time appreciating that, my engine in my car revs at, 6,000 revolutions per minute. That sounds like a big number. Modern processors execute like billions of instructions in a second. And that's why we can do so much. So anyway, that's our basic system there. Okay, so that should all be stuff that you remember. Let's go one step deeper in terms of background, which is thinking more from a program perspective. From the perspective of a program, we start to actually, we said that we have CPU and memory, but a program has a little bit of a structured view of memory. So let's think about what that is. So when I talk about the memory of a program, let's talk about the memory that's accessible of a program, that a program can access. We think of it, and I'll often draw, by the way, this is the sad truth of this class, almost every diagram I do is basically just a rectangle. So there's just a lot of rectangles in this class, and I apologize for it, and you're going to now notice that's all I draw is rectangles. This is how sophisticated we are in computer science. But this rectangle, in particular, I'm going to call something. I'm going to call it the address space of the program. So when a program's running, it has data in memory that it can access. And we call that its address space. And what is an address space? Well, it's very simple. It's just a bunch of bytes. Just a bunch of bytes. And we address it by number. Just like, for example, when you're referring to a particular byte, you just refer to it by its address, which is just a number. And modern address spaces are pretty big. Some can be incredibly huge. We have 32-bit address spaces. More modern systems, we have 64-bit address spaces, which means we can refer to 2 to the 64 bytes. That's a huge number. It's again, with computers, sometimes we get a little bit tricky. We get in a situation where we can't imagine how big that is. So if you, for example, I saw this once, that if you imagine a 32-bit address space, so 2 to the 32 bytes that we can address, if you imagine that as the size of like a tennis court, just imagine this, and a 64-bit address space is something like the size of Europe, right? It's way bigger. Just very hard to appreciate that. But in any case, we have this very simple way of interacting with memory, which is we have our address space, and we can refer to any byte or set of bytes within it by just giving a number, its address. Now, more interestingly, I'm going to erase this byte here, is what we can do here is we can divide up generally what we do is we structure like a running program, like a C program. You'll be doing a lot of C in this class, into a very structured way. We don't just say it's a bunch of bytes. Kind of relating to our discussion of the von Neumann architecture, there's a few things in this address space. Usually we have up here the code. So we have the actual instructions that, you're going to write C code through a compiler. We should take a compiler class so you know how that works. From a compiler, it takes something like C, it turns it into machine understandable code, and puts it, and we're going to put that in memory somewhere, and when we're running, we're going to access it. In fact, a lot of the machinery of a CPU is organized around getting those instructions. You remember things like a program counter, sometimes called an instruction pointer, same thing, IP or PC. Points to the next instruction to execute, and then kind of continues down into certain fashions, again being changed by things like branches or jumps. So code is sitting in there. But there's more to a running program than just code. There's data. And data is structured in a couple different ways. What are some of the parts of the address space that you might remember from 354 or just your general knowledge that are in this address space that store data that's a little more than just data, it's structured in some way? Yeah. Yeah, there's these other two pieces that we tend to talk about, right? We tend to talk about a heap, and we tend to talk about a stack. Now, I will draw for this class, I will always draw it in this way. That means that byte 0 is down here, and whatever the kind of max of the address space is down here. Some people draw it the other way. I find that confusing, so I don't do it that way. That's why it's great to be a professor. You just decide stuff, and then people are stuck with it. So the heap and the stack are dynamically sized, and they change as we go. For example, the heap in a C program, how does the heap grow? When does the heap grow? What has to happen for the heap to grow? Sorry? Dynamic memory allocation. Yes, I can't see where the voice is coming from because I can't see, the masks and all that. We're going to ignore all that. So anyway, dynamic memory allocation, which is done by calling malloc, right? And because you're good programmers, you know malloc has a friend. It's called free. So malloc and free allow us to get some space in our heap, and sometimes the heap has to grow to accommodate that space. What types of things do we put in the heap? Again, this is all reviewed, and if this is boring for you, my sincere apologies. If it's exciting for you, great. And it's somewhere between, well, that's where most people are. So what would you do with memory and heap? What's an example of what you would do? You put an array in there. What else? What are your favorite data structures?
Objects.
Objects! Stop! Sure. So that's like a protest against the fact that we're going to be using C all semester, which is not an object-oriented language. I appreciate the protest, but it is going to fall upon deaf ears. You're using C. The only object you'll have is a struct. You have a structure, and you have functions. That is how we used to do it. Then people came along with all this other stuff. So yes, you can put some kind of structures in there. You can make a linked list. You can make a whatever. Your favorite tree, all the data structures you've learned already. Now the stack is a little more, you can notice here in our running program, this is very much a C-based view of the world, but it's going to be the case that we as a user, as the writer of the code, we are in charge of this. We call malloc, we call free. And we are in charge of what's on the heap very directly in our code. Like you can see it right there. So I would say that some people would say this is explicit, right? It's explicitly, you're doing these explicitly in your code. Stack allocation is a bit different, and I'm going to say it's implicit. It's implicit because things get allocated on the stack. Well, when? When does data get allocated on the stack? Yeah, like when you call into a function. When you call into a function might have, for example, let's say we have some function, returns an int or something like that, some function here, and maybe it has on it, like you're declaring some variables inside of it, ... When you call into the function f, a bunch of stuff is going to happen. And we'll talk more about this in the discussion when we get a little bit more detail. But it's essentially implicit. It's implicit when you call into this that on the stack somewhere there's going to be room for x and y. On the stack there's going to be room for, if there are any parameters to the function, we're going to be able to have, those are going to be allocated on the stack. When you return from that function, importantly, all those things are automatically deallocated. And so that's why it's implicit. Sometimes people call it automatic memory because it's automatically allocated and deallocated as we go in and out of function context. All this should be reviewed. If this is all like sounds really complicated, it's either time to read up or you're going to have a long semester. So my apologies for that. Sometimes I sound harsh. Sometimes I sound harsher than I mean to. I don't mean to. I'm a pretty nice guy. So in any case, automatic memory, implicit, stack, that should all kind of be kind of in your head. Any questions? I'll just review. Okay, good. All right. So that's how a program runs. It gets. Now there's a piece that we kind of didn't talk about, right? We had our very simple model here of CPU and memory. A more realistic model, which I'll just mention briefly, we'll have CPU, we'll have memory. But we also have some kinds of other devices in the system. One we'll talk a lot about is what I'll just call a disk for historical reasons. Let's make some boxes, as I like to do. A disk often is represented by a cylinder when it's a hard drive. Modern systems, you have different types of disks, which are just persistent memory devices. So down here we have what we'll call a persistent memory device, or sometimes people call it non-volatile. And up here we have something that's not persistent or volatile, which is memory. Memory tends to be made of like some technology we call DRAM. Disk can be many different things. It'll be a hard drive if you're talking about, for example, if you work at Google and you're in charge of storing every YouTube video that exists in the world, which apparently there are a lot of, that's what I hear. So if you're in charge of that, you're going to store them on hard drives. And why are you going to do that? I'll actually guess. Why are we going to do that? Why would we have faster, better technologies than hard drives? Why does Google engineers, probably some smart people, why do they choose to store all your YouTube videos on hard drives, not something fancier and faster? Cheaper. That's answered a lot of questions in this class. Cheaper. So yeah, it's 100% cheaper. Hard drives are the cheapest way to store bytes persistently. But we also have other things that we'll talk about in this class, like a flash-based SSD or solid-state storage device, and even more modern technologies are coming out. All these things are happening as we speak, actually, kind of a cool time. So somehow these disks are connected to the system. And when we talk about a program running, usually there's actually some other steps involved. For example, the program, like its compiled executable, usually lives on the disk somewhere at first. Then when you run the program, you're going to load it into memory, right? You load it up here. And then we can start executing it. And of course, it may also store data or access other data on the disk, whatever the disk is, et cetera, et cetera. And of course, there are other things to think about too. For example, there's displays, there's other sorts of other devices that we have to interact with. We'll talk about those at some point during the course. So the picture's a little bit more complicated. For many parts of the class, we can focus on just the CPU and memory. Later on, we'll add in other devices and disks and so forth. Okay. So just a bit of an aside there about a slightly more complex model, which again should already be in your head. Review. Okay. So where were we? We were asking a few questions. You're like, who is that guy? Yes, it's still me, Remzi. How do computers work? Now you know. We have reviewed all of computers. You now know how they work. Congratulations. Now we have to go to this next piece, which is, what is an OS? And I will do this again and bring it down here. By the way, we will also do this other thing in class, which people will remember as the best part of class, which is after this, we will take a short break. So years from now, you'll be like, I don't remember much about this class, but we took breaks, and that was pretty cool. That's what people tell me. I've had a lot of alums tell me that. It actually makes me very sad. So please don't do that. Okay, let's talk about what is an OS. And to do this, I'm just actually going to look at some code. And this is going to be harder because I need to type, and I generally type with my two hands. So I'm not sure what I'm going to do at this point, but we're going to suffer through it. So let's see what happens. Okay, I'm really frustrated by this. This should work. Let me try again. Does this? It doesn't work, does it? Oh, that is so irritating. What? Just attach? Oh, to my mask. This is thinking. I like this. This is the world we're living in. Does this work? I look like an idiot, though. Who cares? You can't see who I am, even. I mean, my face is hidden. Does this actually work?
Yeah.
That is so stupid. Okay, please do not take a picture. Now someone's going to take a picture. Okay, so let's look at some code. I really feel very silly doing this. Okay, fantastic. This is a really stupid piece of code. Can you read it? Yes is a good answer. Okay. First things first, we check if the right number of arguments have been given to the program, and if not, we print out an error message. Fantastic. Good practice. Then, what do we do? What does it look like? You don't even know what spin does. Should I make it bigger, or is it big enough? In the back, are you challenged? By the way, the problem with putting the microphone on this is it's slowly pulling down the mask and my sweating face. And of course, that could be awkward at some point because then it'll be under my chin and I will seemingly be breaking all COVID protocols. So my apologies if that happens. I'm going to need a counterbalance of strings holding up my mask tied to my glasses. So what is somebody guess what this program is doing? And I'll tell you what spin does because we'll just actually look at it. Nothing better than looking at code. People always say you should comment your code, blah, blah, blah. You should just write really clear code first. Then you should comment if needed. Clear code is the best comment. Okay, that's going to be in contrast to what everyone else tells you, so my apologies for that. So spin. What does spin do? Somebody tell me. You say spin for one. What does it do? Yeah. Sorry? Just sitting there spinning, doing nothing, right? Just asking, has it been long enough? So if you say spin for one, it basically waits for 1 second and then sits there and uses the CPU for 1 second, asking what time it is, and then returns. Okay, make sense? Okay, so let's pop back here. So then what does this program do? Somebody else? Nothing interesting, yes. Yeah, perfect. Every second, it prints out the string. Let's see if that works. Pretty exciting. CPU A. We have run our first program in this class. Let us remember this moment. We have run a program. And when a program runs, a program is a compiled, lifeless thing. You compile your C code into a binary executable. That's a program. There's nothing that interesting about a program. It's just sitting there. It's a bunch of bits. When we run the program, we bring it to life. We turn it into what we're going to call in this class a process. And we'll get to this terminology later. But the very earliest people of computing, of understanding systems, invented this term because they realized there's something different about a running program than a lifeless, static program. So a process is running. You can see it's pretty boring here. But there's this kind of amazing thing that we can do. We can actually run many programs at once. In fact, you do this all the time on your computer. What kind of programs are you running? You're running a browser. You're running, I don't know, music. You're watching a YouTube video. You're doing something with Discord, which I don't even know what that is, but we're going to be using it in class. You're looking on Piazza to see if somebody actually figured out all the bugs in the assignment so you can now finally start doing it. You're doing lots of things because you're clever, multitasking, whatever generation you are now. I don't keep track of these things. What generation are the people in the room? Z now? It's so unimaginative. We have X, and then we say, okay, let's do Y, and then we do Z. So what's next? We just wrap around. It's kind of like the X people didn't plan ahead. They're like, let's call this group X. And we're going to run out soon, but okay. Anyway, that was an aside that was not planned, by the way. Okay, so we can run a bunch of programs at once. This is not too exciting because this program is super boring. But we could do it. In fact, we could run hundreds at once. Look, I'm running 4 here at once. And even the earliest computer systems, which only had one CPU, mine of course, my laptop has a few CPUs. Yours do too now. But the earliest systems had just one CPU. I mean, it's amazing. The earliest systems cost millions of dollars and ran much more slowly than any of the computers you've ever used in your life. But that was the beginning of the computing era. And they could run many, many programs at once. So how do you think a system that has only one CPU, let's pretend it has one CPU, and one memory, can run multiple programs at once? Yeah. Something like that. So if you could hear, good answer. It's an illusion. And the illusion for a little bit, then you run the next. You stop this one, then you run the next one, and you stop it, and you run the next one, and you keep going like that. And which system does that? Well, that's the operating system. So I'm going to stop these now. Using kill all, by the way, very useful if you want to kill a bunch of programs with the same name. Kill all. Kill is how you stop things. It sounds a little grim. It's not that bad, but it's what we're doing. So like if we're going back to our note taking here, when we're saying what an OS does, well, from one big task is what we call virtualization. And what that is essentially turning, say, one physical thing, whatever thing is, this is a very precise term, into many virtual ones. Virtualization, okay? In fact, the whole first part of the class will be studying the techniques that people have developed over many decades to virtualize computer systems. What we just saw was what I would call a virtualization of the CPU. So it may seem like we have one CPU, but the operating system somehow switches between all these programs back and forth really quickly and allows this illusion, this beautiful illusion that we have as many CPUs as we need. Okay, so this is absolutely, it's an illusion. But it's a useful illusion, and it's one we're going to see repeatedly in this class. Like I said, it's going to be the first topic that we study, virtualization. You might have talked about this some in 354, which is great, and then we're reviewing. Fantastic. So far we talked about virtualization of CPU. Let's look at another example. Okay, here's a pretty boring program. Let's look at it for a second. Programs will be more interesting in this class. I promise you this is the most basic, boring program. What we have here, again, we're just going to get an argument from the user. And then we have some, at the top you can see, sorry, it's hard for you to see because I kind of scrolled down a little bit. You can see there's a value, it's in memory. And what this, I don't know why this is the pointer P and C, if you remember pointers are just normal variables that store an address inside of them. Here we have the address of value inside of it. Then I print out what that address is. Actually, the address of P itself, and then the address stored in P. So it's kind of two addresses in this program. The address of P itself, P is a stack allocated pointer to an integer. And then we can put out the contents of P, which is an address of value, which is from some other part of your address space. So we talked about a heap and a stack. We didn't talk about a third part of where data lives, which is just like global variables. Data is some part of the address space, usually really top, or the lower addresses in my diagram. And all we do here, well, what does this loop do other than spin? Just adds one to the value over and over again. Right? So when P is an address of value, so it means it's referring to that integer value. And when we look here, we're saying P reference P, that's what a star P means. So take not the value of P itself, but what it points to, add one to it, and then store that back into what P points to, right? And if you're like, oh yeah, C pointers, I hated that, you're going to have a very long semester. So we're going to review that. We're going to even maybe do like a little bit of a C boot camp, working with the TAs on that as we speak. We'll review it a little bit tonight. But absolutely, the one thing you're going to have to do to have success in this class is have a good model of C and pointers and how memory is used in the C program. If that sounds like bad, well, like I said, it's going to be a long semester. So this just updates that value over and over again. So let's do that. Not too interesting. You can see it running, updating the value. And you can also see a couple things. So if you look at the address of P, remember P was allocated on a stack. It was just a pointer to an integer. And because it's a stack allocated variable, when we look at its address of it, you can see it's like a huge number. 7FFEE, huge number, way down in this huge address space. When we look at the address that's stored in P, which is the address of value, you can see it's a much different kind of address. It's much lower, and that's where the global variables are stored. It's in a much higher up in my picture, lower address. Make sense? Okay. Now what's kind of interesting too is we can run multiple versions of this program together too at the same time, right? Let's start 2 instances of mem, 2 processes, same program, but we're going to have 2 different processes running at the same time. And what they do is, well, let's look at it. Okay, that's enough. Now, interestingly, if you look at what they each printed out, in fact, the first thing on the line, I printed out this thing called PID. It's a process identifier. Each running process has a name. And that name is actually just a number. I mean, it's a little bit of a boring world that the operating system imagines. It's like each of you have a name. Great, what's my name? It's 3,000 and whatever. Sorry, 30,032. So, in your running process, your name isn't that interesting. It's just a number. And you can see that the 2 processes are running, they have different numbers. So we can refer to them differently. But you can see they're referring to what looks like the same address, right? They're each referring to the same stack address for P, and they have the same address stored in P, which is that global address of the global variable value. So that's a bit weird. We have one memory. Each program thinks they're accessing those addresses. So what's going on? Well, as you might have guessed, since this whole part of the class is about virtualization, that we're virtualizing, what are we going to talk about virtualizing? We're virtualizing the CPU, and we're virtualizing memory. So you can think of that like this. Each process, which is again just a running program, has the illusion of its own CPU and its own memory. There's only one memory in the system. It's addressed from 0 to whatever the size of the physical memory is. How much DRAM you bought? How much DRAM is in a modern system? Some number of gigabytes, right? 16, whatever, 32, 8, 16, 30, whatever. Some number like that. I mean, that number makes me feel old too, because when I was in graduate school in a different century, I was very excited because they're like, you have a new workstation. It costs probably like $15,000. It's on your desktop. It was a huge TV in my face, which made me slowly go blind. And inside the computer was a processor it was an exciting milestone for computing. It was a 1 MIPS processor, which means it executed 1 million instructions per second. And it had something like 1 megabyte of memory. So we're a bit off of that. It's quite a bit, quite a bit has changed in this time since. But the basic techniques of virtualization actually haven't changed that much. And what we have here is this beautiful illusion that you have your own memory for your own program. And when we switch and we're running a different program, it has an illusion of having its own memory. We're going to learn exactly how that works. There's a bunch of mechanisms, policies, all this cool stuff that happens underneath the hood of an operating system to make that work. Okay, so virtualization. In fact, virtualization, I organized this course into 3 pieces. And you may have noticed in the textbook, it's called 3 Easy Pieces. You'll agree with at least 2 of those words. There are 3 pieces. It may be easy. That depends on you. It may be some other words that people have used to describe the pieces. That's up to you. You can keep that amongst yourselves. The first piece is virtualization. Okay? I'm going to look at one more piece, and then we'll take a break so we can revive. It's hot in here. My face is sweating. I'm doing this stupid thing with the mic. But let's just do that. Let's just look at one more piece. The second piece. Okay. This is kind of cool. Okay. How many of you have written a multi-threaded program of some kind? Okay. Why did you do it? For fun or because the class made you? Fun? What else? Class?
Lab.
Oh, a lab you worked in. Okay, cool. So someone did it for work, someone did it for fun. Did any other reasons that people wrote a multi-threaded program? Some passion. Okay, I don't know. People do things for lots of reasons. So a multi-threaded program, it's kind of this interesting thing. You'll be writing multi-threaded programs in this course. You can think of it like this. We're going to not understand this fully today, but it's kind of like having one process that's running that has a bunch of independent activities happening inside of it at the same time. And so we can think of, for example, and where that's useful, there's a lot of reasons that's useful. We'll talk about that a lot. But one of the reasons it's useful is you can write a parallel program. That's one reason, for example. So let's say you have some tasks that you want to do, like, take an image and transform it, like apply a filter to it. You can, for example, take parts of that image, create what we call threads, or these little independent activities inside the program. You can create those, have them each kind of do a transformation on a part of the image at the same time. And if you have multiple CPUs on your system, which most do, it'll run faster. So parallelism is one reason we have these multi-threaded programs. And if you don't know what this means, that's totally cool, no big deal. Okay, so let's look at this multi-threaded program. Now, what we're going to do at the beginning is we're going to create what are called two threads. Okay? And this is going to be the second part of this course. It's about what we call concurrency. We're going to create two threads, and you can see the third argument to that pthread create or die routine, which is called the worker, and that says what function to start running these threads in, which is this worker function up here. And you can see what this worker function is doing. It's just updating a counter loose number of times. Okay? Does it make sense? So if we pass 10 to the worker, 10 loops, right? Then each worker will update the counter 10 times. So it goes from 0 to 10, for example. So if we have two workers, which we do here, and this is how we create two threads, which is called create. And create or die just fails if pthread create. It's a not error around pthread create. And then join just waits for the threads to finish running. That's just a term. Join comes from history of multi-threaded programs. It's just waiting for the threads to complete. So we wait for them both to complete. So let's say we gave each thread 10 loops to run through. They're updating the same counter. And let's say we told them each to update the counter 10 times. What value should we print out at the end of the counter? Using our friend multiplication, two threads, they each update 10. What number should we print out? Who is a bold math adventurer who's going to multiply 2 times 10? Yeah, okay, no, that's the answer now. I remember that. It should print out 20. Does it make sense? Any questions about that? Okay. Quick question? No. Okay, let's see if what happens. Works. So these threads each kind of update the counter 10 times. Does that make sense? Okay. So let's do it a little longer. 100,000 times. What should this print out? Yeah, mumble. That's exactly right. So somebody answered. What should it print out? I know, it's a dumb question. I'm just going to wait. 100,000 times 2. Yes? Okay. Let's see what happens. Hey, is this computer broken? Let's run it again. Huh? One more time. It'll probably get it right on the third time. That's what I've learned. Oh, no, it didn't. Okay, we have a problem. Threads, and these threads are creating some new problems for us in creating programs that work correctly. We are really used to one thing about computers. They're deterministic. And they produce the same output when we do the same thing over and over again. But when we create multi-threaded programs, some very interesting interactions happen. And now we're not going to understand deeply why that happens today, but I'm going to give you a hint of why it happens. And this is the second part of the course, which focuses on threads and what we call the topic of concurrency. What happens when you have a lot of stuff happening at once? Here we have these, so topic 1, virtualization, topic 2, concurrency. And what's happening is we have thread 1 over here and thread 2 over here. And what they're each doing is they're trying to update, well, let's look at that code for a second. They're trying to update that counter, right? They're doing this counter ++ repeatedly. And they're updating the same counter because they're threads, they're operating on the same data. They work in the same address space, right? So they're not independent programs operating on different data, which is what separate processes do. They're the same piece of code, the same operating on the same data in the same address space. And the problem that's happening, I'm just previewing this, and we're going to understand this very deeply later in the course, is to do something like a counter plus plus. Well, what kind of assembly instructions might that look like? What does that look like at an assembly or instruction level? Yeah, so there's certainly an add in here, but there's often actually an instruction sequence, right? Like there might be a load of some kind, and then an add, a load, say, of the value of the counter into some sort of register, then maybe an add of 1 to that register, and then a store of that register back into memory. And that's what's happening over here, too, in this other thread. And what happens once in a while in this multi-threaded program is that the two loads happen at the same time. So you both load, say, the value 10. You each update it independently to 11, and then you each store back the number 11. So instead of adding twice, we've essentially added 1 in parallel at the same time. So we haven't accomplished what we've tried to do. Now, if we don't understand that, that's okay. We're going to get into that in great detail. And the coolest part about the concurrency part of the class is absolutely you're going to stare at like 4 lines of code and have a hard time understanding it. Because it's very hard to imagine all the possibilities of threads running through code sequences at the same time. So we can actually readily address this. And those of you who have written multi-threaded code understand there's this thing we call, it's called a lock. And what a lock does is when there are multiple threads trying to enter a piece of code at the same time, what the lock does is make sure that only one can get in there and do the right thing, which is to update the counter. So even though both threads are trying to do it at the same time, that's a problem we're going to encounter, and we're going to solve it by putting locks around these pieces of code and ensuring only one thing can happen at a time. And so when we run this version of the code, version 1, it should just always give the right value, regardless of how many times how long we run the program for. So there's much to learn about threads and concurrency. It's absolutely intellectually the hardest thing we're going to do, I would say, in this course, and it requires us to think of it differently. There's a question.
So would locking slow the program down?
Yeah, fantastic observation. Would locking slow the program down? General answer is generally yes, it would. It's going to make it, in this case, that only one thing can happen. So when we're structuring a program, if we want it to run quickly and in parallel, we have to think about how to divide things up so that they can run independently and they aren't constantly locking and unlocking and competing. And that's when you're writing a program like that, you often think about these synchronization issues that they're calling. How do you get the threads to work in harmony and have a lot of parallelism, perhaps? This happens inside the operating system all the time. When people are trying to design operating systems that work well on many processors, they have to think carefully about the data structures they have to make sure that they're not constantly being stuck on this one lock trying to access it all at the same time. So we'll get into that, but absolutely good observation. Other questions? Yeah?
For D0, could you have had each thread add to its own variable and then add its variables at the end instead of blocking?
Yeah, fantastic question. So the question is, couldn't I have just done this in a better way? Could I basically have 2 separate counters, have each thread update, I mean, it's kind of a silly program to begin with, but you have each thread update each independent counter, and then kind of after the threads are done, kind of just add those 2 together, and therefore kind of get the work to happen in parallel. And absolutely you could do things like that, and when people think about writing parallel programs, they think about strategies like that. How can I divide this work so that we don't have to synchronize all the time? Absolutely, and we'll talk about some examples of that. Of course, we can't get into too deeply because we're just going to touch on some of the basics. Yeah?
This blocking rely on special instructions on the ISA.
Great. Another really good question, and then after this we'll just take a brief break. Does locking, what time is class at? 6:45? I've waited way too long for this break. This shows that I have not taught this class in a few years. My extreme apologies. So maybe we won't take a break. No, we'll take a break. So the question is, does locking require special instructions from the instruction set? And the answer is yes. The short answer is yes. And we'll talk about those instructions and what hardware support we need to build locks correctly. This is something that people realized very early on in computer systems. That the first systems that were building, they were trying to figure out how to build a correct operating system. They realized they needed more powerful instructions. and just loads and stores. It's really hard. There's some people that did some work on how do you do it just with loads and stores. It's very hard to do. So modern systems all use special instructions, and we'll talk about those. So way too late in the class. We're going to take just a brief break. My apologies. We'll come back in like 3 minutes, so just stretch, see your old friend from across the room, wave, say hi, and we'll come back.